Okay, very good. Welcome, everybody. We're very happy to have Bartek Czech from Tsinghua University, who made an effort to tell us what does the Chern-Simons Formulation of AdS3 gravity tell us about complexity. So this is the second installment of the new series, Tensor Networks in Quantum Field Theory.
Okay, so thank you very much for letting me speak here before a global audience. This is work in collaboration with Zizhi Wang and Bo Chen, who are my students. And also, this collaboration started, this work started from some very impactful conversations with Michał here. So maybe he is not a co-author, but he is the godfather of this project. So I want to, the title is, what does so-and-so tell you about complexity? So let's first talk about what our expectations of complexity are. So the first point will be complexity. Before I tell you about complexity, there must be a zero point, which is complexity of what? So I have to start with the question, what is a state? So a lot of the times when we talk about complexity, we have on mind a pure state in some Hilbert space. But of course, we might have to describe, and probably will have to describe mixed states as well. And in that broader context, the following definition of a state, I think, is most robust. I'm going to make a table here, where in the table, I will have the first column of the table is observables, and the second column of the table is the expectation values of those observables. And so in the first column, what I should list is a complete set of observables that comprise the algebra in which the algebra of observables in which I am working. So if I'm talking about a CFT, then a complete set of observables would be, for instance, the set of primary fields inserted at some particular location, maybe descendants, such as this. And then I would have various things listed here over, I would have to have different entries for different conformal representations, which are present in my theory. I also would have observables which look like bilocals and trilocals, and so on and so forth. So what I listed here is the full set of things that I may want to the full set of things whose expectation values I may want to compute in the CFT. So the answer to the question, what is a state, is that a state is a machine which takes these observables and returns expectation values. So a state is something that takes this observable and it returns an expectation value. If I happen to be talking about the ground state of a CFT, then we know that one-point functions of state are 0. One-point functions of descendants are also 0. These two-point functions will be delta 1, 2 over x to the 2h. That's the value of the two-point function. Three-point functions also have some known value that I will not bother writing. But the point is that a state is characterized as a map from the set of observables to a set of real numbers, which are their expectation values. So a summary of this statement is that a state is a map of the form trace row ... This is what a state is. And this definition of a state is used in a lot of places as a matter-of-fact definition. Most notably, quantum information theory people typically describe a state in this form as a map from observables to real numbers. So, I don't know, are there any questions at this point? If there aren't, then having said what a state is, we can now tackle the question, what is complexity? And complexity must be a way of figuring out what the entries in this column are, given a set of observables that I have. That's what complexity must be, because that's the set of quantities that characterize my state. Preparing a state means finding out how to fill in this column of expectation values in the table. So now let's think about filling in this table, and I think about what the complexity of a state defined in this way should be. The typical paradigm for talking about complexity is that there is some reference state, and out of this reference state, I'm going to apply unitary gates, and those unitary gates are going to prepare my state. So this paradigm envisions that there is some first column in this. Table. Let me see, maybe blue will be pretty clear. This third column is the expectation values in the reference. Okay? The reference itself has some values over here. And then the idea is maybe I can use unitary gates for given my characterization of the reference, maybe I can go to the values in the table that I actually want, which is described the state that I'm really talking about. So let me put this back, the definition of a state, a straight row, ... That's what a state is supposed to be. I have to say that I find this way of thinking about complexity a little awkward. In general, I think that to fill this table, I shouldn't have to start from some other way of filling the table and just update the entries. I might as well just fill in the table myself without starting from a reference. And so that's the point number one that I want to make here concerning complexity. So for complexity, I'm going to start listing some observations or some expectations that I have of the concept of complexity that I would like to match. So the first thing is I need to fill the table. The second point here is that maybe filling the table by updating some pre-existing table is maybe it's not the most efficient way of doing things. So you might ask, what is an alternative? An alternative is maybe there is an algorithm which tells me, given an observable, what I should put here. So if I have some algorithmic way of filling the table, which doesn't just start from some pre-existing values of the reference and update them, but actually generate these numbers by themselves, then I would like to say that that algorithm is our key to what the complexity of the state is. So the second thing I'm going to write here is search for an algorithm. And then the third thing is, given that I have an algorithm, assuming that I will find an algorithm, talk about the algorithmic complexity. In other words, how hard is it to actually carry out the algorithm and fill in the entries in the table? This program is the program that I would like to, first of all, promote in general. I would like to promote this way of thinking about complexity. And my goal for the talk today is to give you an example of how this kind of program for complexity can be carried out in practice for a particular state. That particular state is the vacuum of a two-dimensional CFT. Are there any questions about what I said so far?
I have a question. You say that you want to find the complexity of some algorithm. Like, do you want to find the minimum complexity of all kinds of algorithms? Because, like, for generating these tables, there could be in principle an infinite set of algorithms that generate all these
Sure.
expectations.
So we have to agree, probably, okay, on a level of a theoretical discussion, we would have to agree on some principles for what operations are the basic operations in the algorithm. That's a little analogous to choosing the set of gates in the usual circuit model. But I don't want to enter that level of a theoretical discussion so far, at this point at least. I would like to just give you the example first, and then you will judge for yourself whether that's a sensible notion of complexity that I want to present. So that's just my proposal for now, but I am agreeing with the sentiment of your question. We have to agree on some rules along which we will quantify the complexity of different algorithms. And once those rules are set, presumably we have to choose the complexity of the most efficient one.
Yeah. All right, thank you.
Any other questions or comments? But what I really want to convey here is that a state is a machine for generating expectation values for all kinds of observables. And when I say it this way, it's a little artificial to start from some reference, which already has some expectation values, and go from there to the state that I want, if in fact I could just fill the entries of that table by myself, without reference to some, well, reference. I'm going to make two more comments about why I think this way of complexity is beneficial. So when we're talking about the complexity of pure states, we usually imagine that the reference is going to be a completely unentangled state, and our job in life in preparing the state is just to entangle this initially unentangled state until it is the state that we want. So we're going to apply some unitary gates, and those unitary gates are going to be producing entanglement until I get the state that I want. So I do have two conceptual problems with this picture. I just want to put it out there. And you will see that this way of thinking is immune to those two problems that I have. So one problem is, what about mixed states? If I want to describe a mixed state, then, well, first of all, I can't be starting from a completely unentangled pure state. Unitary gates are not going to turn my pure state into a mixed state. The most natural thing you may think about is that maybe I can have a completely a mixed state version of a completely unentangled state, namely the identity matrix. The identity matrix is like the simplest matrix I can come up with, which would be the simplest theoretical density matrix I can come up with. Notice that thing is very different from, I think this is the simplest reference that you can imagine for generating a mixed state. But even then, you will not be able to apply unitaries to generate an arbitrary density matrix. You have to have some object which generates different, or changes the spectrum of the density matrix, and that's not present in the unitary model. So that's one problem that I see with the usual unitary circuit approach. And another approach is the actual choice for the reference. If we go back,
can I actually comment on this issue? So of course I agree with part of your criticism. I just want to point out that in the circuit complexity business, there's been developments dealing with generating state using unitary time evolution. So partly Hermitian and unitary gates. And you can use these gates to generate, for example, a thermal density matrix in various ways and optimize over these various ways of preparing thermal density matrix. And of course, we can purify, right? And you can discuss generating mixed states purifications and using unitary gates or like whatever gates you want, right, to generate these pure states.
So is the method to construct a pure state, which is a purified version of the density matrix that I want? And
yes, yeah, so there's a double minimization optimization, right? There's optimization over, first you have to consider all possible purifications, as inconceivable as it sounds, right? And then for each purification, you have to find the one that optimizes some definition of complexity.
Okay, so this is So this is a model which uses unitaries plus one extra operation, which is tracing out.
Yeah. I mean, I don't want to enter the discussion. I just wanted to put it on the table.
Yeah. Okay, so I am willing to concede that one of my worries is maybe already completely solved. Then I have another worry. The other worry is that if I think about the state as a map from observables to their expectation values, then let's take the reference that people usually like to discuss, which is the completely unentangled state. A completely unentangled state is going to have some completely crazy numbers in this reference column. It's the state which is maximally poorly behaved in terms of the expectation values of various observables that I can consider. And so my second worry is that it's difficult for me to believe, maybe that's how nature works, but it's difficult for me to believe that the relevant notion of complexity is build this table of well-behaved and well-understood values, starting from another table which has all kinds of crazy and insane and infinite values. That's the kind of worry that I have. And well, yes. Are there any responses to it? Let me just ask. So, assuming that there are no, actually, I probably shouldn't invite too many responses because I don't want the talk to degenerate into a discussion about this point. I just wanted to signal that issue. The approach that I am about to illustrate here will not have that issue. Okay. So, so that's the idea for complexity that I want to have. These are these points 1, 2, 3. There's actually a fourth point that I should add here, which is if I'm talking about states in the holographic context, then the complexity of a state is obviously going to depend on the cutoff at which I'm working. So we all know about the proposals for complexity, the volume proposal, the action proposal, and all of them depend on how far the state goes out, or how close the state goes out to the description of the state goes to the asymptotic infinity. So there is always a cutoff dependence of any notion of complexity, and that's a statement that preparing a state at cutoff 1 is different from preparing a state at cutoff 2. So there must be a cutoff dependence in my notion of complexity. So as I am illustrating, as I'm giving you my notion of my proposal for how we can think about complexity, I want to satisfy this way of thinking about it. But in addition to it, you should ask me: do I have some way of incorporating a cutoff, and especially in a holographic context, does my notion of complexity depend in some way on at what cutoff I'm working? So I'm just going to put here cutoff dependence, and that's a desirable feature of any proposal that I have to make for you. Any questions or comments? If not, then I will actually go to the meat of the talk.
Yeah, I just have a comment like about the cutoff dependence. Like once one is happy with the cutoff, right? Then I mean this issue of observables being badly behaved in the reference state, in your favorite spatially disentangled reference state, might be gone.
I don't think it will be completely gone because, as we all know, that's actually what firewalls reminded us of, although this was known before. That if I want to take a state and rip it apart into pieces which are unentangled, then I will create some infinite energy at the point where the two pieces are joined together. And the completely unentangled state is going to have that infinite energy everywhere. So I think that that issue is not really cutoff dependent. The cutoff is going to come, huh?
There's always a question how you regulate your Hamiltonian way.
Yeah, there is a, yes, so there are.
I just want to point out that it seems so.
Yeah, so if we try to regulate it, then what we're saying is that there is some column of the table, the reference column, and that reference column, maybe I can use an appropriate regularization prescription to make it well defined. I'm always, I want to convey my philosophy about this. In my view, this is worrisome because we just keep adding more and more ingredients and sort of have a moving target. That's my worry. I'm not saying, actually, I just want to be clear. I'm not saying that what people do is wrong. I am saying that I'm worried about it and I'm trying to propose an alternative which doesn't have those problems, and then time will show if the alternative is correct. Okay. So the title was, what does the Chern-Simons formulation of gravity tell me about complexity? So I told you about what type of complexity I want to get. Let me now give you a very brief reminder of what the Chern-Simons formulation of AdS3 gravity is. And then using this Chern-Simons formulation, I'm going to give you a definition. Here I'm giving you a plan for the rest of the talk. Then I will give you a definition of a state, which is a definition compliant with this notion of a state. It is I will tell you what a state is as an algorithm that generates the entries in this table. And then we will discuss together what the complexity of that algorithm is. This will go back to the question that Marius, I think, asked. And hopefully I will be able to convince you that we know how to count the complexity of that algorithm, and then we'll see what happens. So that's the plan. So first, the Chern-Simons formulation. So I start with some completely amorphous three-dimensional space, which has coordinates x plus, x minus, and u. That's just names for coordinates. And the statement is that describing a geometry or a metric and a spin connection on this space parameterized by x plus, x minus, and u. It is to do that, to give you a metric and a spin connection, I have to give you two SL2R valued gauge connections, which are called A and A bar. These are SU2 gauge fields. What does it mean that they are SU2 gauge fields? It means that every component of A and A bar is some linear combination of the familiar L0, L1, and L-1 generators of SL2R. So just to illustrate what I mean, I'm going to write an explicit solution for these A's and A bars. So one of them is L0 du over u. So this is the u component of this field, and the value that the u component takes is L0 over u, which is a member of the SL2R algebra, plus L-1 dx plus over u. And then A bar, I have to choose two of them, will be minus L0 du over u. And I believe here there is a minus sign, L plus 1 dx minus over u. So here is some example solution. I have two gauge fields, and both of them are valued in the SL2R algebra. And I will erase this part of the board now. And the formalism tells me that once I have chosen some the fields A and A bar, I can write down from them and immediately tell me a metric for this space parameterized x plus by x plus, x minus, and u. And the metric has the form 1/2 trace A minus A bar squared, which maybe if I write it in coordinates, this is going to be clear. So the metric is 1/2 trace A minus A bar mu, A minus A bar mu, dx mu dx mu, where mu and mu are plus, minus, and u. So there is also a similar formula which involves a plus a bar for the spin connection that I have here, but I will not have any particular need for it in this talk, or so I will just more or less disregard that part. A more complete story I would have to tell you would involve the spin connection, but we will not use it in this particular talk. Okay, so I just owe you one more explanation, which is what do I mean by these traces? So the traces are taken in the fundamental representation of SL2R, and that means that trace L0 squared is 1/2, and trace L plus 1, L minus 1 is given by, I think, -1. So with this prescription, I can just take these fields A, and I can see what components, I can take any mu and mu component. This gives me some quadratic in the algebra of SL2R, and then I can take the traces of those quadratics, and that will give me the metric components. So for this particular solution, which I wrote here, if I follow this procedure, then the answer will be dx plus dx minus plus du squared over u squared, and we recognize this as the pure AdS3 solution. So this solution represents pure AdS3. If I had chosen some other solution, then I will be describing some other geometry. I need to tell you
clarification: are you Lorentzian or Euclidean?
This is Lorentzian, as you see. There's a pair of light-like coordinates. So I need to tell you two more things about this gauge field. One of them is that I don't know where to write it anymore. One of them is that having a so far I just told you that if I choose some A and A bar, then I will get some metric. So is it going to be an arbitrary metric? No. So here is a point of key importance, which is that Einstein's equations are equivalent to A and A bar being flat. And okay, is that clear? If I choose A and A bar so that it's flat, then I have then the resulting metric here will obey Einstein's equations. And then the second point I wanted to say is that this is a gauge theory. So you can ask, what happens if I perform a gauge change? I just go from one gauge to another gauge without changing the physical solution. And the answer is that this corresponds to applying a diffeomorphism here. So the gauge freedom that we have here is essentially the freedom of choosing coordinates on this space. So long as I'm not changing the physical solution, changing gauge is just changing coordinates. It's just diffeomorphism on this, applied to this geometry. Any questions or comments? Is everything clear so far? Okay, so in any Chern-Simons theory, the observables that I have, or the objects with which I can play, are Wilson lines, first of all. So I drew this space here, which is parameterized by x plus and x minus and u. Now I know that there is some gauge field which lives inside here. And what I can do now is to compute a Wilson line that begins and ends at some point. Now, I didn't tell you about boundary conditions for this thing. So I just told you that if I change gauge, then I'm applying diffeomorphisms. But as we know, in three-dimensional gravity, if I apply, I'm only allowed to use diffeomorphisms that vanish at infinity. If my diffeomorphism doesn't vanish at infinity, then that so-called large diffeomorphism is not an actual diffeomorphism, it really changes the state of the theory. So to discuss a particular geometry, I have to agree that I'm going to be changing gauge, but not at infinity. So that means I have to have some boundary conditions for A and A bar if I want to specify a particular geometry. If I don't obey boundary conditions, then I have the freedom of actually changing geometries in my three-dimensional gravity. So there will be some boundary condition that A and A bar have to satisfy, and that boundary condition in effect decides what geometry I will have in the bulk. Okay. So why did I just mention this? Well, first of all, it will be important in the rest of the talk. But second of all, because I'm talking about these Wilson lines, so here I chose the Wilson line with these points, which if you're willing to see this, this is a Wilson line that begins and ends at asymptotic boundary. So I'd like to contrast it with some Wilson line that begins and ends in the bulk. A Wilson line that begins and ends in the bulk is gauge dependent, because I can change gauge in the bulk, and so I can have any value for the Wilson line that I want. But if my Wilson line begins and ends at the boundary, then it's a gauge invariant object. Of course, I could change it by doing gauge changes at the boundary, but that would be changing the state, and I'm fixing my boundary conditions at infinity. So therefore, the Wilson line will be a gauge invariant. In this setup, a Wilson line that begins and ends at the boundary is gauge invariant. So the basic objects that I get to play with in this theory are Wilson lines that begin and end at the boundary. Okay, so let's try to evaluate one such Wilson line and see what happens. I'm going to, well, here's the first thing about evaluating these Wilson lines. Remember, I just told you that my A and A bar are flat. The fact that they're flat means that I'm free to deform the Wilson line everywhere except at its endpoints. So this Wilson line is the same, and this Wilson line is the same. And in fact, this Wilson line, which goes entirely in the boundary, is just as good for evaluating the, well, it gives me the same outcome because of flatness. So to evaluate the Wilson line, I can just pass it from the beginning point to the end point without ever going into the bulk and staying in the boundary. Okay. So let me just write what this is. A Wilson line that begins at some point xi plus and goes to some point x final plus, okay, is equal. And I will write what it's equal to in a moment. Let me just make one more comment, which is I only concentrated on the plus coordinates of my endpoints. So this would be the plus coordinate of the final and initial point. That's because one of my fields only depends on x plus, the other one of my fields depends on x minus, and these fields don't talk to each other. And so I can do the computation of a general Wilson line in two steps. First, the x plus dependence, then the x minus dependence. The x plus dependence only picks up contributions from A. The x minus dependence will only pick up contributions from A minus. So here I'm just focusing on half the story. There's another half of the story which will build up from A bar. But in the x plus, to capture the x plus dependence of the thing, I have to write a path ordered exponential from xi plus to xf plus. And here what I have to do is to insert this piece of A. Okay, in general I would have to take the path ordered exponential of A. But because I'm moving only along x plus, that A is the thing that I'm pointing in is just this component over here, which is L minus dx plus over u. And this is my Wilson line. Any questions or comments about what I have said so far? I'm gathering that there are no comments. Are we still hearing each other?
Yes, everything is working great.
Okay. So let's just say in words what this object is. So L minus 1 is the generator of translations in the CFT. Yes? And when I exponentiate it, what I'm generating is a finite translation. And this is a finite translation by what amount? By the amount x plus final minus x plus initial discounted by u. Yes. So if I'm really working at the boundary, then u would be 0. So these translations would be by an infinite amount. But we expected this because when I'm doing translations at the asymptotic boundary, I'm always moving by infinite amounts. And I just have to somehow scale out this u dependence to get a sensible physical result. Alternatively, you could imagine that to get sensible physical quantities, I shouldn't actually be taking the Wilson line all the way to the asymptotic boundary. Maybe I should stop it at u equals 1. And that's equivalent to working at a particular cutoff. And then I would just have to agree that my boundary conditions are not set at infinity, but set from infinity all the way to the value u equals 1. I could do that too. But the point is that I get this finite translation. So this is some SL to R transformation, but it doesn't tell me all that much about any CFT quantity so far. Remember, my goal is to fill in the entries in the table which I have erased, which will tell me how to generate expectation values of observables. Exactly, expectation values. So this is an SL to R transformation. What I have to do is to take an expectation value of this SL to R object. So let's do that. I will erase this part of the board now, unless there are any pressing questions or comments about it. So the key thing that we want to do next is to somehow take expectation values of this Wilson line. So I'm going to write again Wilson line xi plus xf plus. This is an operator, and now what we need to do is to take expectation values of it. So here's an example of an expectation value I may want to pick, I may want to look at. I'm going to choose these Wilson lines carry different representations of SL2R. And different representations of SL2R are just different conformal families that are present in my CFT. So with this notation, I want to look at what is the expectation value of the Wilson line in the state which is the primary state in the representation H of the conformal symmetry. Is that clear? I could also put descendants here and compute expectation values in descendants, and I can choose any H that I want. Choosing any H that I want is equivalent to declaring that this Wilson line was actually a direct sum of all representations in a direct sum of all representations present in my CFT. That's what that would be. So so let's compute it. To compute it, I have to give you some rules about what these H's are. So here I have a representation. Okay, I have learned that my Wilson line is a finite translation. What I need to tell you is how to think about these states X and the H. And the best way to think about them is to go from them to the position basis. So you may or may not know, although you all know this actually because this is how we do CFTs, that a representation of the conformal group of conformal dimension H can be represented, one representation for it is in terms of functions of some variable, such as x, and those functions have to satisfy the following properties. So the state H expressed in the x basis is just 1 over x to the power of 2h, that's that. And then when I want to generate descendants, so if I wanted to consider L minus 1 acting on H and express that in the X basis, well then I just have to tell you what L minus 1 is. And L minus 1 is the usual minus dx. And then there are some expressions for L0 and L plus 1, which have minus x dx and minus x squared dx. We're familiar with this. But then there are some extra terms here, and those extra terms account for the different conformal dimensions that I can have. So I think what I put here is h, and what I put here is plus 2hx. I don't remember what actual corrections I have to put here, but the point is that these corrections account for what conformal dimension I am actually talking about. Plus, the information about h also enters through with what function I represent the primary. So primary is this, and then the descendant would be minus ddx applied to this object. A second descendant would be minus ddx applied twice to this object, and so on and so on. So different states in a given conformal representation are represented by different functions of the variable x. There is one more thing I need to tell you, which is we see an h hat here. I have to tell you what an h bra is. And an h bra turns out to, in the x representation, turns out to be the delta function. All of this stuff, you can take my word for it, or you can open various papers. The paper where I learned about this is the paper by Liam Fitzpatrick and Jared Kaplan and some collaborators about OPE blocks for the Virasoro group. But I'm sure there are many other sources where this is explained. So with this set of rules for how to evaluate this expectation value of the Wilson line, it's actually applied. So I went here to the x basis. So if I go to the x basis, that's equivalent to inserting identity in the x basis. Inserting identity in the x basis is like saying x. Okay, this is just identity in the x basis. Now, having inserted this, I can put this x over here and this x over there. And I guess I need another set of x's. I have to put them both in this place and in that place. That will express my Wilson line in the x basis. It will also express the h and the h in the x basis. So when I do this, I will get something which looks like this hx becomes the delta function. That's what I learned here. This Wilson line is that finite translation by x plus f minus x plus I over u. So let me just write it as e to the negative x plus f minus x plus I over u, L minus 1. And this object is acting on xh, which is 1 over x to the 2h. This is an integral which I have to evaluate, and when I evaluate this, I will get the expectation value of my Wilson line. So what does this do? This is a finite translation which shifts x. So this is the same as an integral of the delta function stays here, 1 over x minus x plus f minus x plus I over u. And this object is raised to the power 2h. The delta function sets x to 0, and what I have is x plus f minus x plus I, and there is a u over here to the power 2h. What is this object? Well, thinking about a CFT, what this object is a two-point function of a primary field of conformal dimension h, which is inserted at x plus f and at x plus I. So we have learned is that this Wilson line actually computes a two-point function in a CFT. Are there any questions at this point? I guess there are no questions. Okay. So if you didn't follow the details of this calculation, they're not tremendously important. The important point that to be conveyed here is that this Wilson line that we considered, a Wilson line that begins and ends at the boundary, computes a two-point function. That's very good news for us because remember we wanted an algorithm that will compute expectation values of all observables, and one class of observables we already know how to do. That's two-point functions. Two-point functions we know how to compute with these Wilson lines. So it looks like the Wilson lines are going to be useful as a generator of these expectation values. Maybe if I can just harness the power of Wilson lines to compute higher point correlation functions, then I can maybe construct a machine that will fill in all entries in my table, and that will be the algorithm that I'm looking after. And that's exactly what I will do next. Any questions, or shall I tell you about higher point functions now? So let me tell you about higher point functions now. So obviously for higher point functions, simple Wilson lines are not going to do. I need something that depends on 3 points. And so I'm again going to draw my x plus, x minus U space. We already talked about Wilson lines. But now, let me talk about an object that depends on 3 points. And what these 3 points are some 3 points on the boundary, which we'll identify with locations in the CFT, dual to my ADS space. And I want to, compute the 3 point functions of these things. So each one of these Wilson lines, I imagine, carries some representation, which is H1, H2, and H3. And I want to compute a 3 point function of operators with conformal primaries with conformal dimensions H1, H2, and H3. So if I just connect them, then I got my 2 point functions, so that's not very good. So evidently I must find some way to join this line over here. So that means that the object that I need to supplant now is a junction. Okay. Now remember, so I must introduce a new object to the game, which will be a junction, something that either takes 3 incoming Wilson lines and sends it to a number, or conversely, maybe it takes 2 incoming Wilson lines and generates 1 outgoing Wilson line. That's the kind of thing that I want. Now, in principle, I can define it in any way I want to, but some definitions are much worse than some other definitions. So let's think about what would be a very good property. A very good property, thinking back about Wilson lines again, is that if I had a Wilson line like this, then I was allowed to deform it, and I was allowed to deform it because of the flatness condition. So it's very natural to ask of my junction, the new object I'm describing, that it gives me the same flexibility, the flexibility to deform the Wilson line network that I'm trying to describe. So if I can come up with a definition of a junction which allows me to deform this network into this network, then that's clearly a very good thing to do. Okay. Essentially what this means is that the junction itself has to be a gauge invariant object. Yes? So now let me ask you, how would you construct a gauge invariant junction of 3 Wilson lines? What does it mean for it to be gauge invariant? It means that if I do the same kind of gauge change, so if I simultaneously change gauge on all 3 legs of this junction, then the object is invariant. That's gauge invariant. Okay. On the other hand, if I just change gauge on one of the legs, then I have turned an incoming representation from, let's say, a primary to a state in a representation from a primary to a descendant. So that kind of thing means that on any single leg, the junction must be gauge covariant and not invariant. It has to covariantly transform under SL2R. That's the only way it can incorporate changes of data such as, do I have a primary or a descendant coming in? So the junction, let me tell you again, has to be gauge invariant under simultaneous gauge changes of all 3 legs, but gauge covariant under just a single leg. this set of words is exactly the same set of words that defines the OPE expansion in a CFT. Or said differently, it's the same set of words that defines free-point functions in a CFT. A free-point function is something which is covariant under SL2R transformations to apply to any one particular field. But if I do the same SL2R transformation to all fields, then the free-point function is obviously invariant under SL2R, and so it doesn't do anything to it. So the statement that I want to make here is that these junctions, if they're going to make my Wilson line network deformable, they have to, what they have to do is to do OPE fusion in the CFT. That's the only way I can choose them. Okay. So I could write some equations which describe what this junction is, but I think it's not very useful to write the equations. The point is that my Wilson lines, the Wilson line junctions, are doing the same job as the OPE fusion does in the CFT. That's the thing that I want. So with that choice of a junction, it is more or less immediate that if a Wilson line computed a two-point function, this junction is going to compute a three-point function. Because it takes these two things, and then at the moment when I go out, pass a junction and go to the third thing, it's like I have applied OPE fusion to join these two representations and make it into one, thereby reducing the rest of the calculation to the calculation of the two-point function. That's exactly how you would compute a three-point function by applying the OPE in the actual CFT. Okay. So, so the bottom line of this discussion is that Wilson line networks compute higher point functions in the CFT. And there is nothing sacred about a three-point function. I could apply one other junction and make a bigger Wilson line network like that. And this object, with two junctions and four coming lines, would be a Wilson line network which computes a CFT four-point function. And if I joined one more line, it would be a five-point function, and so on and so forth. And so what I want to convey to you now is that Wilson line networks with arbitrarily many junctions compute correlation functions in the CFT of arbitrarily many local operators. Any questions or comments about that? So now we are ready to talk about what the state is. Remember, the state was a map which takes an observable and returns the expectation value. So I'm going to draw for you an object in ADS. I will stop drawing these boxes and I will just actually draw an ADS cylinder because we're talking about an ADS space anyway. I'm going to draw for you what object in this language does exactly the same job as this map, which sends observables to numbers. And this object is this. Okay. What this is a network of Wilson lines, which was designed to compute some very large point correlation function, except that I have truncated all the legs. Why is this this object? Well, it's this object because what this object is doing is taking some observables and returning a number. Now, taking some observables means taking a Wilson line which carries some SL2R representation and joining it here and here and here and here. And after I have joined all of them, this thing will give me a number. And what is that number? That number is the correlation function of the Wilson lines that came in here, of the appropriate conformal representations. So this is exactly the machine that we're looking for, which returns expectation values given an observable. Now you might say, I have some particular number of truncated legs here. So won't this only compute for me an 87-point function? What about the lower point functions? And the answer is that's easy. All I have to do is to bring in a a Wilson line here, but that Wilson line will carry the trivial representation. That's like computing an expectation value of O1, O2, and then the identity operator inserted someplace. Okay, that's like a lower point function. So this thing computes for me all endpoint correlation functions in the CFD. Any questions or comments? So if not, then I want to say one more thing about it, and then we'll talk about what the complexity of this object should be. So the one more thing about it is that notice that this thing is not gauge invariant. Oh, Michał has a question.
Yeah, I have a question. Do you have something to say about other solutions, like these solutions that are diffeomorphisms of AdS?
You mean large diffeomorphisms or small diffeomorphisms?
Well, I mean the ones that do not vanish asymptotically, of course.
That do not, yeah. So sure.
We can also respond it later.
Yeah. So we can probably talk about it offline because I've talked for almost an hour. So, but it's not a problem. Let me tell you about diffeomorphisms that just act in the bulk, because that's a point that's more important to my story. So let's say that I change gauge. As you know, I already told you that changes of gauge correspond to changes of local diffeomorphism in the bulk of AdS. So you might say, oh my God, this object is not gauge invariant because I have all of these truncated legs which end not on the boundary but in the bulk. So this object is not gauge invariant. And that makes perfect sense. Why does it make perfect sense? Because to turn this into a number, I have to truncate it with some Wilson line which comes in from infinity. And this Wilson line has an interpretation of taking a representation from the extreme UV of the CFD and bringing it over to the IR. But so the fact that I have some gauge dependence over here is the statement that if I bring in a representation from the extreme UV to the IR, I can get it in any SL2R frame that I want. And that is not surprising, because there is no God-given unique way of applying RG to SL2R representations. If I give you some operator in the UV and I say bring it over to the IR, then you may just apply some the exponential of L0 and just change scales. But what you can also apply is some combination of L0 and L-1 and L+1 on the way. And that means that as you're bringing it from the UV to the IR, you're also doing a little bit of a translation and a little bit of a translation in the inverse coordinate, which is fine. So the statement that I want to make is that applying RG flow is not something that we expect to be gauge invariant, only gauge covariant. This is really clear if I think about fields which are spinning. If I have a spinning field, then it's characterized by some polarization. So theatrically, I'm going to raise my hand and say, this is my polarization, and I'm in the UV. I'm going to come to the IR. So I can do it this way, and I'm not doing any polarization changes. But I can also do it this way. And nobody stops me from applying some local symmetry, which is in my little group, as I'm going from the UV to the IR. So that's the statement that RG is not gauge invariant, but only covariant. And the fact that this truncated network is gauge dependent is the statement that it takes in gauge dependent inputs. And so that's why we expected this to be true. Okay. Okay. This brings me to another point, which is that the location of the network is something that's actually fixed. Why is it fixed? So I told you that Wilson lines can be moved about, but the moment I truncate this thing, then the truncated network cannot be moved about easily, because it wants an input that comes at a particular location. Well, the only thing I can do is to possibly take this wide network that I drew over here and deform it into this kind of yellow network, which has the same stubs, okay, but it joins these things at different scales. Well, if I do this, this is like applying RG to my state, to the map itself. That's what this redrawing of the picture would mean. So the location of the network in the bulk of my AdS cylinder tells me what cutoff I am using in the definition of the state. I drew it here, that means I'm working at this cutoff. If I go to another location, that means that I have changed my cutoff and gone to some coarser scale. Yeah. Any questions or comments about that? So, in the final, I don't know if I can talk for another 5 minutes, but if I can, then I will tell you about how go back to the plan of actually, well, this was supposed to illustrate what complexity is. So I just told you so far what a state is, and it's a state of a given cutoff. Let me just tell you about the complexity of it. So remember, this thing so this is, as I promised, a machine that takes observables to real numbers. And I wanted to say, I want a machine which works like an algorithm, and then I will quantify the algorithmic complexity of this. So let's think about how this machine works and what steps it takes. Well, we understand exactly what steps it takes. It merges consecutive Wilson lines at these junctions, and the only thing that happens is really applying the junction over and over. So going back to Marius's question, how am I going to judge which operations are harder or easier and so on? Here I just have a single type of operation, and so I'm just going to count the number of applications of that single operation. This Wilson line is my algorithm, and it consists of applying the same junction over and over. I'm just going to count the junctions. And so that's the algorithmic complexity of the algorithm I have exhibited. So I want to say complexity is the number of junctions. So you might say, I can put my junctions at any density that I want. Sure, so the complexity is not even well defined. But I want to take a different take on it. So that's a viable thing to say. I want to have a different take on it, which is everywhere so far in the discussion, I have been applying this this SL2R Chern-Simons formulation. What does it mean? That we have gauged the local isometries of AdS. SL2R cross SL2R is the group of isometries of AdS3, and we're taking the isometries extremely seriously in applying this formulation. That the isometries are the only thing that we're playing with. So I would say that if there is some notion of counting how many junctions I can have here on this truncated Wilson line network, it has to be an SL2R invariant. It can't be an SL2R covariant, and it can't be arbitrary. It should be an SL2R invariant. Now it turns out that there are only 2 SL2R invariants for a given curve in the bulk of AdS. I'm lying a little bit because there is a third one. Let me just focus on the 2 which are easy to illustrate. When we incorporate the third one, it doesn't. Well, let me just tell you. You have learned in differential geometry that a curve in 3 dimensions has 3 vectors that are attached to it everywhere. One vector is the tangent to the curve. That's like velocity. One is acceleration. That's like how the curve is turning in space. And then there's a third one, which is torsion. That tells me how the plane spanned by the velocity and the acceleration vector, how that plane itself is changing. So I'm going to ignore the torsion part here, and I will just focus on the acceleration and the velocity. Okay. That's effectively what we'll be doing next. So I want to say that if we want to estimate what the number of junctions could be, then this number of junctions, or really the density of junctions, per unit length on the curve. So this is the proper length of the curve. And instead of saying d junction ds, let me just say d complexity ds, because that's what I really want. Okay? So a density of complexity per unit length of the curve. Okay? I'm saying that there are essentially only two things that can be on the right-hand side of this equation. A third one is torsion, which I will ignore. So one thing is it could just be a constant, and the other one is that it could be the extrinsic curvature of the curve. There's also the torsion thing, which I am ignoring. The torsion is for a later discussion, but I will not have that discussion today. So these are the only options which are consistent with the isometries of AdS. So if there is, that's an if there is a meaningful notion of quantifying how many junctions I can have here, so what the complexity is, that notion boils down to just choosing these two numbers, C1 and C2. So in the remaining -5 minutes that I have, I'm going to try to convince you that C1 is equal to 0. So in fact, this term is not even there. So let me just tell you why that is. Let's consider a surface like this, so a truncated Wilson line network like this, which follows a curve which has 0 extrinsic curvature. If I have 0 extrinsic curvature, then I'm only sensitive to this coefficient. Yes? What's a curve of 0 extrinsic curvature? It's a geodesic. And so let me ask you, how many lines do you expect to have on this kind of network if the network follows a geodesic? And I expect 0. The reason why I expect 0 is that my cutoff surface goes all the way to the boundary, and so it actually defines a cutoff. If I had more than one thing here, then that would imply, if I had more than one truncated length here, it would imply that I could bring Wilson lines over from here, more than one, and so I would have more than one place where my representations could originate from within a single cutoff surface. That's completely contradictory to what I even mean by a cutoff. A cutoff is someplace where I can only have a single piece of data, not several pieces of data. And so this is the argument that I want to use to conclude that if I have a geodesic cutoff surface, then I should have 0 complexity. So C1 must be 0. If C1 is 0, that means that d complexity ds is proportional to the extrinsic curvature, and that means that the full complexity has to be proportional to the integral of k ds, the extrinsic curvature integrated along the length of my cutoff surface in the bulk. And now the Gauss-Bonnet theorem tells me that this thing is equal to the volume inside plus some small correction that doesn't matter very much. And so this volume here, so if you buy my argument that C1 equals 0, then the complexity of this object is volume, and it's the volume that lives here. And so we have recovered the volume proposal for the ground state of the complexity of the ground state of a two-dimensional CFT. And that's all I had to say. So hopefully this is a good illustration of my philosophy about complexity. I am advocating, think about the algorithmic complexity of constructing the state, and maybe that's a better approach to complexity, at least an approach worth considering. So thank you very much.
Thank you, Bartek. Super. Thank you very much. Do we have some questions from online? Let me start with these.
Hi, do you hear me?
Yes.
Yes. Maybe I have a very simple question. So your proposal was that you have this, in a sense, the integral of the extrinsic curvature along the curve, right?
Yes.
So why could it be the square or something like that of the extrinsic curvature?
Excellent question. So a priori, it looks like I could construct, because the extrinsic curvature is an invariant, therefore I could imagine constructing higher powers of k, and that's dimensionally off, but I could kill off the extra dimensions with powers of LADS, which I just have sitting around. So in principle, that's a possibility. This is the problem with that option is that it doesn't have a well-defined limit, as I am making my my curve. Oh, maybe the other way around. It cannot be discretized in any way. And so imagine trying to discretize the, that's maybe an extra assumption that we may want to have. Imagine trying to, taking an integral such as k squared times LADS integrated along the curve, and imagine trying to discretize it. Then if I approximate my curve as a sequence of little geodesic segments and discretize the curve this way, then the extrinsic curvature will be infinitely concentrated at just the corners where the geodesic segments meet. And so this object, integral of k squared, is just going to blow up. And this illustrates the point that that the integrals of higher powers of k are in principle well defined for smooth curves. But the moment I'm trying to distinguish between a smooth curve and an identical looking curve that consists of geodesic segments, they will be vastly different. And so I am assuming that the notion of complexity we want is not sensitive to whether I draw my curve as smooth objects or little geodesic segments joining together. That's an assumption I make.
Okay. Maybe I should say the motivation I was asking was that a few years ago there were these proposals for how to calculate holographically entanglement entropy in higher curvature bulk theories. You know, these papers by Xidong and Chern-Simons.
Sure.
So would you argue, I mean, they had these kind of proposed functionals with like extrinsic curvature squared terms.
For computing entanglement entropies.
Yes, as the functional that would have to be extremized. So would your argument, or would your argument work against those proposals too? Would you be skeptical about those proposals for the same argument?
No, because not that. So I don't think that these arguments intersect each other very much. In the case of Xidong and other people's work, the minimal surface, which becomes a minimal of some other functional in higher derivative theories, that is something that sort of nature gave us, and we're trying to describe it. Whereas here, we are choosing our cutoff, and the idea is that our choice of a cutoff shouldn't be it shouldn't depend, the complexity shouldn't depend very much on whether I drew my cutoff very smoothly or with little corners. So anyway, in this case, the formula is supposed to quantify something that we put in as input, whereas in their case, like, they have finite answers manifestly. So, and anyway, we're not, because I'm not talking about how to compute entanglement entropies here, I think that there is no real intersection of these two questions.
Okay, thanks.
We have some further questions online. Okay, then I have a question. So is there a relation with the works that Janet Han was doing at Theorem with collaborators?
Joanna who?
Janet Han, Lingyang Han.
Oh, what is that work? Maybe I don't know it. I think I would know it, but
no, like she has papers about tensor networks in p-adic AdS3. Well, I was just wondering if you were.
I know those papers, but what is the connection with?
I was asking if you see any connection or not.
Okay, so I'm not aware of any connection, and I would have no idea how to relate it to p-adic AdS3. So if you have some idea about how to do it, I'm very curious. I'm not aware of any relation.
Now, do you have something to add about tensor network part, given the topic of the meeting?
So this is a, oh, thank you, because this is a tensor network line of, yes, series of thought. So notice that we have this thing in tensor network language. What kind of tensor network is it? It's a what is it called? It's an MPS state. So this truncated network of Wilson lines that I am proposing to be the avatar of the state is actually a matrix product state, because I'm applying the same operation and over and over and over to construct the state. What is that operation? It's the OPE. And so by the way, you might ask, this is not about the MPS-ness of this, but I forgot to say this. You might ask, so I just gave you some algorithm for computing expectation values of observables in the CFT. Is that a sensible algorithm? And the answer is, that's how any of us would compute a 5-point function in a CFT. You would just apply the OPE once, and the second time, and the third time, and then you would be done. So that's what this thing is doing. So I think it's a very reasonable and sensible algorithm. Yeah, that's what I wanted to say. Now, returning to the MPS-ness of it. So it has the form of an MPS state. So you might ask, why is it that I gave you this MPS state, and let's say Vidal or other people have spent so much of their lives trying to give a tensor network description of the ground state of a CFT? Couldn't they have just written an MPS state and be done? And the answer is that on each one of these lines that I have here, I have all possible representations that are present in the CFT. So this is effectively an infinite bond dimension MPS state. So the whole point of, let's say, Mera was to turn this MPS state into something that could do an equally good job with a finite bond dimension. And that required closing in this network into the bulk in some way. Now, as you know, I love Mera equals kinematic space kind of pictures. So maybe I shouldn't even be talking about closing it in. I'm going against my own philosophy in doing that. But the point is that constructing a tensor network that isn't an MPS has something to do with filling in this bulk. And so, but if I don't want to fill the bulk and I want to stay on the boundary of my region, just at the cutoff, then I have to do an MPS state with infinite bond dimension will do. Or I can have an MPS state with some finite bond dimension, but then it will have well, it will have errors that are well known for MPS representation. So I am taking from this a sort of meta lesson that the way holography works is that it fills in these spaces inside, and it fills in these spaces in a way that, from a computational point of view, makes the tensor networks more efficient, because I am not taking keeping track of arbitrarily high energies and masses as I go along, as I would have to on the boundary. In the bulk, things are sort of done more smoothly, and that's the job of a tensor network that has loops inside it, like Mera. I don't know if these comments made any sense to anyone but me, but that's how I think about it. I think it's a nice picture, if it's true, of what holography does. It like allows us to get away with a smaller bond dimension for the same kind of state.
And like one more question. So like, I mean, I understand that this discussion like largely or maybe even entirely relies on the special features of AdS3 gravity. Do you have some ideas for generalizations to higher number of dimensions?
Yeah, so let me, first I'll make a comment that this work was more or less ready in September, and the reason why we haven't put it out yet is that we're hoping to, in one go, publish a version that works, that answers Michał's question. But we probably will just put out this paper in a few weeks because this thing will take longer than we thought. So this question is harder than we thought. But yes, we do have definite ideas for what to do next. So let me say this. Let's say that I was talking, and I will explain the idea in just a few sentences. Let's say that I was not in the CFT ground state, but in some in a state created by a primary from the vacuum. So if I was in such a state, then you might ask, does anything differ about that situation from the ground state? And the answer is essentially no. I would still be able to compute all correlation functions in my primary state, also using the OPE over and over. But from the AdS gravity point of view, I should have some back reaction and the volume should be different. So somehow just applying the OPE fusion over and over is not the answer in general. It only happened to be correct in the vacuum. So what do we replace it with? And so what should the junction do in a different state? And so here is the tentative answer. The junction must be joining or merging objects which are natural on the cutoff, on a given cutoff region. This cutoff region is given by the entanglement wedge. So what really we should be doing is joining modular zero modes on different cutoff sized regions, and that's what the junction should be doing. Now, in the special case of the ground state, modular zero modes are given by OPE blocks, and OPE blocks are, joining OPE blocks is the same as just applying the OPE, so that's why this worked. But in a more general context, we expect that we should be taking modular zero modes of cutoff sized regions and merging them, and that has a good chance of working in any geometry. And then the information about the geometry would be, what are the zero modes? Whatever they are, they're always localized on the cutoff surfaces, on the individual cutoff surfaces.
Actually, on my WhatsApp, I just got a question from somebody who doesn't have a microphone in the laptop. But the question is basically if you are aware or see a direct relation with the work of Serra et al., who constructed an MPS representation of CFT ground state using vertex operators. It also has
no,
one dimension.
I'm not aware, and I want to have that reference so that I can. Yeah, I am not aware, and thank you for this point. And Michał got the message, so he will relay to me put me in contact with the person, or at least send me the message.
Okay, so a chance to ask like one last question, and I think we're gonna call it a day. Okay, if not, let me. Oh,
it's 4 minutes to midnight in Beijing, so we have 4 minutes.
I think it's also a good idea to call it a day. Anyway, thank you, Bartek, for having this talk, and
thank you very much for having me.
So late. Thanks everybody else for joining in. A quick announcement: we're gonna continue after the winter recess in January, and I think the next speaker is gonna be Frank Strata. So please stay tuned. We're gonna send email announcements in due course. Thanks.
Thank you.